Rising oil prices, depleting resources, and pollution have forced humanity to look into electrical cars more seriously than ever before. And now they have become a part of the future that we envision. In fact, they are our present now. Unlike regular cars that have IC engines, which are bulky and polluting, electric vehicles have electric motors, which are much simpler and much cleaner. To understand how they work, we have to understand the electric motor in its simplest possible form. And that is what we are going to do now. Here we have the schematic of an electric motor in its simplest possible form. What we have here is a magnet or two poles of a magnet. We have a coil which has a current circulating through it, and it is the interaction of this current and the magnetic field which causes a motor to work. To understand how this happens, let us consider first the rectangular loop PQRS that is fixed along a central axis. Now, there is a current I flowing through this loop, and it is kept in a uniform magnetic field B, which is perpendicular to the magnetic field lines. Now, we know that all magnetism comes from currents, and so the current carrying coil here is acting as its own magnetic dipole. The current in this loop PQRS is causing a small magnetic moment given by small m, and the direction of this magnetic moment is perpendicular to the plane of this coil, as we can find using the right hand thumb rule. It is also, in this case, parallel to the direction of the external magnetic field being given by the magnet. Now, the magnetic field B exerts a force F on each arm of this current loop. So, we see that this is a rectangular current loop. There are 4 arms, and each of these arms will have a current, and as a result, there will be a force being exerted on that particular arm. For example, FPQ is equal to IB times capital B, and so on. Now, each of these arms gives the direction of the respective forces acting on them. Since these pairs of forces are equal and opposite, they will cancel each other out and form a stable equilibrium. In other words, in this condition, this coil is not going anywhere. In this case, the net force as well as the net torque caused by the magnetic field in the loop and outside is equal to 0. Now, if we impart a small rotation to the coil in the magnetic field such that the magnetic moment small m is no longer parallel to the external field capital B, but instead at an angle theta, the situation changes. In this case, the forces acting on each arm of the loop still remain equal and opposite as before. So, the net force is 0, but there is a difference here compared to the previous case. The forces on the arms PQ and RS are not in the same line of action, and as a result, there is a torque tau generated due to this mismatch, and this is in the clockwise direction. Now, the torque generated by the system can be given as force multiplied by perpendicular distance, and that perpendicular distance is the distance from the axis to this arm. Now, viewing along the side A of this loop, we can find the specific values to find the net torque acting on the current loop. So, here is the total torque acting on the current loop due to various causes. This is the force exerted on the arm PQ, this is the force exerted on the arm RS, and since torque is the force multiplied by the perpendicular distance, this figure here, A by 2 times sine theta, and here gives us the perpendicular distance from the axis of rotation of this motor, and thus this gives us the total torque acting on this motor. As you will see, both torques have the same sense, hence both torques will add into each other. Thus we see that the total torque becomes equal to IAB times capital B sine theta. Now, substituting the value for magnetic moment in equation 5, we get the new equation for torque given as I times capital A times capital B sine theta, where A is the net area of the rectangular loop. This means that the torque tau is the cross product of the magnetic moment of the coil and the magnetic field. If you examine equation 7 closely, you may find it very similar to another equation. Yes, this equation is very similar to that for torque acting on an electric dipole in a uniform electric field. Now, if you remember that class, you will know that the amount of torque acting on the dipole is dependent on the angle between the dipole and the external field, and the same is the case here. Coming back to the case of the magnetic dipole, we understand that for various values of theta, that is, various values of rotation of the coil, we will get various values of torque. As theta tends to 0, the perpendicular distances between the forces FPQ and FRS reduce to 0. There is no offset between them, there is no misalignment between them. So we get a scenario where the net force and torque acting on the system is 0. In this case, the magnetic moment M of the coil is parallel to the external field capital B. This system is at its most stable state in this position, and any disturbance to this equilibrium will create a torque, bringing it back to its original position. So this is a stable equilibrium. The coil will experience its maximum torque when the magnetic field moment M is perpendicular to the external field, that is capital B. So in this case, theta will be equal to 90 degrees, and we know that the sine function, sine theta, maximizes at 90 degrees. So here we have tau is equal to IAB sine theta, or simply tau is equal to I times capital A times capital B. Now, when the magnetic moment is anti-parallel to the magnetic field, in other words, M is pointing to the opposite direction of the external field B, the torque is again 0 as theta equals 180 degrees. But you could ask, how is this different from the earlier case where theta was 0 degrees? Well, unlike that case, at this time, the system is in a very unstable equilibrium, which means that even the slightest disturbance to the system will cause it to rotate back into its stable state, to its equilibrium state. Electrical motors have multiple windings, so obviously things are not as simple as we have shown in the previous example. In this case, let us say that it contains n number of windings. So n coils are all acting together in the same direction. So in this case, we multiply the magnetic moment by the number of coils in the system, that is given by capital N. So small m becomes equal to capital N times I times A. Now, since torque is equal to the moment of the coil small m times external field B, increasing the number of turns also scales up the value of the magnetic moment of the coil and thus increases torque. This is why all real-world motors have a huge number of windings to maximize the torque that is possible. The principle you have learned here is basic to all DC motors. So, if you have a motor running off a battery, it is working on this principle. So, by scaling up the amount of torque available from these motors, we can use them for aircraft, we can use them for high-performance race cars, motorcycles, all kinds of weird and wonderful applications are now possible. So let's summarize what we have learned so far.
Manorama Horizon, learning made simple.